In this lab, we're going to be testing the stoichiometric ratio between species in a reaction by reacting a solution of copper-2 sulfate with solid iron. In this case, a single displacement reaction will occur where the solid iron will dissolve into solution, becoming iron ions, and the copper that was in solution will precipitate out as solid copper. By measuring the mass of the original iron and copper-2 sulfate that we use, and then measuring the mass of the final product of the copper, we can determine the percent yield for this reaction, or alternatively the percent error for the predicted mass of the product. To start this lab, what we're going to do is measure out the mass of the copper-2 sulfate into a beaker. And by taking our beaker right on our scale, we can measure the mass of that beaker to be 66.24 grams. And then what we'll do is add in our copper-2 sulfate until we get to 12 grams of copper-2 sulfate added into the beaker. So the mass of the 66.24 gram beaker is very important, as we will be measuring the final mass of the product copper in that beaker. So we're going to tare our scale. Now reading 0, we can take the beaker off and we can start adding copper-2 sulfate to the beaker. Remember that we add solid to the beaker or to the weigh boat off the scale instead of on the scale, because we don't want to spill any chemical on the scale and damage the scale. So we're 9.67 grams. And while this may take some time, it's an accurate way of measuring our mass and keeps our scale from becoming damaged. .71, and if we pass the 12 grams, we can remove some of the copper-2 sulfate and place it in a waste beaker. So for example, 12.66 grams, put my lid on my copper-2 sulfate, we can take this and we can place extra copper-2 sulfate into a waste beaker and bring it down to the required 12 grams of copper-2 sulfate. You'll notice I don't pour it straight into the waste beaker, just in case I still need to use some of this to get up to 12 grams of copper-2 sulfate. We get 12.00 grams. Taking our copper-2 sulfate, we will be adding 50 milliliters of water. And placing that on a hot plate, we'll heat up the solution while also stirring the solution, because the copper-2 sulfate needs to dissolve to form almost a saturated solution. So we use a magnetic stir bar in this setup, and we turn on our magnetic stir bar to start stirring the solution gently. I don't want to stir the solution rapidly to splash, so we want to make sure that this is stirring at a lower rate, and have the heat turned on to slowly warm the solution. While that's stirring, we'll take the time to weigh out the iron that we'll be adding to this reaction by again taring the scale, this time placing the weigh boat on, taring it once more, and now weighing out 2 grams of the iron, in this case filings, into the weigh boat. Now, weighing out iron filings is not as easy with the shaker bottle instead of a scoopula, so I will pour in what I think is 2 grams or more, and we can use the scoopula to scoop out excess iron filings into a separate weigh boat designed for excess iron. Very close. Too much. Just right. Now if we take a look at the solution that's stirring, we can see that most of the solid particulate has dissolved. You can take that off for a second and take a look. And we could see that the solution seems to be fairly homogeneous. So what we can do now is we can turn the stirrer off, turn the hot plate quite low because we will be using that in a second, so I don't want to turn it off. And we can remove the stir rod using either forceps or alternatively another magnet to pull the stir bar out. So I'll use forceps and place my stir bar into a wash basin. Now what we can do is we can take our iron solid and add it to our copper 2 sulfate solution, slowly stirring as we add it in. And once it's all mixed in, we'll stop stirring and allow the newly formed particles to settle. If you see any solid on your stir rod, make sure to rinse those quickly into the solution, as every single piece will be weighed and be used to calculate the moles of the product formed. At this point we can already see that copper has formed in the beaker with the reddish color. However, we will let it sit for 5 minutes to complete the reaction and to settle onto the bottom. We're now prepared to do the decanting. So we'll take a big waste beaker here, and to decant it's to carefully pour off only the top layer without disturbing the solid inside. Now I can see that there is quite a bit of solid floating around the top. So I'm going to decant very slowly and gently, and my stir rod is going to catch some of that solid particulate matter. And then I'll rinse my stir rod back into my copper solution here. So I take a look, and most of the copper is sitting right there at the bottom of the beaker. And what we'll do now, you can see all that copper there. What we'll do now is we're going to rinse the copper in this beaker with distilled water. So what we're going to do is stir it up a little bit again. And then we're going to allow another 5 minutes of settling as it dilutes the copper 2 sulfate solution down. We'll do this rinse several times in order to remove all the copper 2 sulfate solution. And we can see that it's a lighter color than our decanted product here. So we're going to rinse this several times, and then after it's been rinsed successfully several times, we're going to end up drying the copper on the hot plate. We're now ready for the second stage of decanting. So again, we will carefully lift this and pour just the solution layer off the top. We use the stir rod here with the properties of water and adhesion so that instead of splashing, we can pour gently into the stir rod and therefore not lose any particles by pouring out very quickly, and also to not make a mess splashing. And we can see the copper is becoming more purified as we go. So we're going to do another rinse using distilled water and getting down the sides of the container. This will be our final rinse here. So we now let that settle one more time in order to allow it to decant a little easier, and then we'll dry our copper. At this point we're going to decant for the third and final time, gently pouring off this top water layer. I'm not sure if the camera can zoom in far enough to see, but there are sometimes tiny little bits of copper that are floating and therefore coming off with our decanted liquid. What do you think that would mean in terms of our final calculation? And there we have a small pile of copper. So what we'll do now is we'll place it on the hot plate and we'll allow it to heat up to dry the copper. So we don't want any water there at all because of its extra mass. So we're going to dry this very well in about 5 minutes on the hot plate, and then we'll weigh it on the scale. Our copper is now done drying, and so what we can do is take the beaker and place it on our hot plate and record the mass on the hot plate as 68.52 grams. That's the final mass of the beaker plus the weight of the mass of the copper on the inside. So of course you'll need to subtract the mass of the beaker that we started with, the dry beaker, from this mass in order to get the mass of the copper produced. You can then go ahead and calculate the moles of copper, or like I said previously, conversely calculate the percent error. If you could predict the mass of copper that should have been produced from the 2 grams of iron that reacted. Or you could also calculate the percent yield. Now, alternative to this heating method to dry, if the solution of copper needed to be filtered, an apparatus similar to this could be used in order to filter. Now, this general setup is termed a filtration apparatus. It consists of a funnel, okay, and that funnel sits in a ring clamp, and the funnel neck is actually going to touch the waste beaker there where the filtrate will be poured, right at the bottom. Now, why is it important for the funnel to touch the beaker? Again, think of the properties of water and the concept of adhesion. You then take a piece of filter paper and folding it twice form a cone shape. And then opening up that cone shape will provide you a filtration area. So placing it inside the funnel, the easiest way to keep it inside the funnel is to use just the slightest amount of water on the upper edges of the funnel. And what this does, again, using the properties of water and the concept of adhesion, is it sticks the funnel right to, sticks the filter paper right to the sides of the funnel. You could then take, I'll use my waste as an example, but you could then take your mixture of copper and copper and solution and pour it through, again using the stir rod, and noticing that it does drain fairly slowly. So don't overfill your funnel, just make sure it touches the beaker in order to stimulate that drainage. And you can pour very slowly and allow the solution to drain through the filter, leaving any solid particles behind in the filter paper. And the solution that makes it through the filter and ends up in the waste beaker is called the filtrate. And in future lab experiments, if you need to test the ions that are present in the filtrate, you could test them by adding a precipitating ion to it and filtering out any of the precipitate into a filter, and then retesting the filtrate to see if any of those ions are still present or to see if other ions are present. So either using a heating drying method, as we did with the copper, or a filtration method, as we're doing here with our waste beaker, either one would collect your solid and dry your solid. The filter paper would need to be laid out to dry, and once the filter paper is dry, you'd weigh it similar to the beaker there, of course having tared the filter paper and recorded the dry filter paper mass before beginning this experiment. Either way, we collect the mass of our final product and we compare it to the theoretical calculated mass of our product using stoichiometry.